Hello everyone, my name is Carlos Andujar from Birbic UPC in Barcelona, and today I'm going to present this work, which is about the creation and optimization of navigation techniques for the immersive web. This paper is a joint work with Ahmed Kamal, who implemented this platform as part of his master thesis. Let me start with a quick overview. Navigation is one of the major user tasks when interacting with virtual environments. And although hundreds of interaction techniques have been proposed to navigate through 3D scenes, 3D navigation still poses a high entry barrier for many users. Virtual reality devices allow for a more immersive exploration of 3D worlds, but navigation in VR is challenging for many users due to potential usability issues related, for example, with specific controllers, user skills, and motion sickness. In this paper, we discussed the design of a test platform to facilitate the creation and fine-tuning of navigation techniques for the immersive web. The key idea is that we provide ready-to-use versions of the most common navigation metaphors like walking, flying, and teleportation, and we allow users to customize every single aspect of these techniques to the point of being able to specify the exact mapping between user actions and virtual locomotion. We will show that this method facilitates the adaptation of navigation techniques to specific people, scenes, and applications. First of all, why should we care about navigation for the immersive web? In the last few years, we have seen a substantial evolution of the different technologies that allow people to experience 3D virtual environments. Thanks to the advances in laser scanning and photogrammetry, the digitization of objects, buildings, and sites has become a common practice in many fields such as cultural heritage. The web is the ideal platform for the dissemination of these 3D models. Since the web is open and based on well-defined standards, anyone can publish content, which in turn can be accessed by anyone. Furthermore, web browsers exist for many platforms, including computers, tablets, smartphones, TVs, and even VR headsets. Actually, VR headsets are the focus of this work. Many VR devices today are supported by the WebXR Device API, which provides a platform-independent way for accessing these VR and AR devices. So as I mentioned, 3D navigation is an essential task when interacting with 3D scenes, and usually the first thing we do when we open a 3D scene is to navigate. So is 3D navigation an already solved problem? Well, I don't think so, although there are some cases where navigation is easier than other cases. On the one hand, navigation difficulty depends on the type of a scene. When the 3D scene is just a single object, navigation is easier and it can be accomplished with just rotate, zoom, and pan interactions. But when the 3D scene is more complex, for example, a building, navigation is harder. Users can become disoriented and fail to explore the parts of the scene they are interested in. On the other hand, navigation also depends on the platform being completely different for non-immersive devices and virtual reality devices. For virtual reality devices, the navigation technique plays an essential role in the user experience. On the positive side, room size tracking allows users to inspect the scene by just walking, and that's the most natural option, but of course it is limited to a small-scale exploration, let's say up to a few meters. For medium and large-scale exploration, we need a proper navigation technique. On the negative side, in VR, every single application has its own navigation technique. There are a few navigation metaphors. For example, teleportation and flying, but the actual implementation of each metaphor is unique for every game if you consider all the details and specifically which user input is considered and how this input is mapped onto user movement with respect to the 3D world. Actually, interaction techniques for 3D navigation have received a lot of attention. A recent study has identified and characterized over 100 navigation techniques used in virtual reality. The reason for such an increasing variety of navigation techniques is twofold. On the one hand, VR software and hardware are in constant evolution, opening new opportunities for 3D interaction, for example based on eye tracking and hand tracking. On the other hand, current interaction techniques for navigation have important limitations, which bring us to another key factor for navigation difficulty, which is the user. I mean, user skills, experience with 3D and VR, and motor capabilities. Actually, some works have pointed out that there is an inherent trade-off between accessibility and simulation sickness. In other words, if the navigation technique mimics real-world movement, you minimize motion sickness, but you make your application less accessible to people with limited mobility. Conversely, if the navigation technique departs from real-world movement and embraces a more abstract mapping, for example, just pointing or looking, then we increase accessibility, but we also create discrepancies between visual and vestibular stimuli, which might result in user discomfort and motion sickness. So we can conclude that no universal technique for VR navigation exists that works well for all situations. As we have seen, the suitability of a specific navigation technique depends on many factors, for example, the virtual environment, the target platform, and the user profile. We believe that there is an increasing need for more exploratory studies of VR navigation techniques and more mechanisms to facilitate the adaptation of existing techniques to specific hardware, environments, and users. For example, those users for which VR navigation poses a high entry barrier, people with no experience in 3D or VR navigation or with motion disabilities. So what's our contribution? We present a method to facilitate the creation, adaptation, and fine-tuning of interaction techniques following the major navigation metaphors, I mean teleportation, flying, and walking. At the core of these interaction techniques is the mapping of user input onto user motion, although other components also play an important role for the user experience, for example, the addition of techniques for alleviating motion sickness. We will describe our experience with a web platform using JavaScript, WebXR, and 3GS for adapting interaction techniques based on these navigation metaphors. In particular, we designed the platform to support easy experimentation with interaction techniques for navigation, where developers can easily create and test new mappings through user-defined custom functions, easy customization to particular 3D scenarios, and similarly, we wish to facilitate the adaptation to people with no experience on 3D navigation, for example, art historians willing to explore a virtual museum. Let us quickly review the previous work on VR navigation. Virtual locomotion techniques can be roughly classified into walking-based, steering-based, and selection-based techniques. Walking-based techniques, such as walking in place, mimic the natural ways of moving around. These techniques include real walking as well as other techniques involving repetitive motor actions such as arm swinging. Steering-based techniques provide a continuous control of direction, which can be controlled using the user's body, for example, gaze, hand, torso orientation, or through physical steering props. Selection-based techniques greatly simplify navigation by letting users focus on where to get instead of how to get to a specific location. A widely known selection-based technique is teleportation, which moves the user to the chosen destination either instantly or gradually. A proper design of the navigation technique could be the difference between enjoying the presence of being in another world or suffering discomfort, disorientation, and nausea. Common methods for alleviating motion sickness include field of view reduction and independent visual background. Some techniques, such as instant teleportation, lack optical flow and thus are unlikely to trigger motion sickness. Turning to our approach, we propose a tool to facilitate the design, testing, and fine-tuning of navigation techniques for virtual reality. Our tool is based on the following premises. First, we believe that adapting the navigation technique to a specific scenario can improve the user experience. For example, a narrow cave in a factory might require completely different navigation techniques. We also think that adapting the navigation technique to specific user profiles, for example, art historians, or functional abilities of the users, can make the application more inclusive. And fine-tuning the different parameters and design options that define a navigation technique can make a large difference. Very often the devil is in the details, and a poor choice of some parameter can make a navigation technique usable in some specific scenarios but unusable for the rest. Finally, all these adaptations are effective if they can be implemented and tested in an easy way, with nearly immediate iteration cycles, with a complete control of the mapping between user input and locomotion changes, and with arbitrary runtime modifications. We support two different levels at which designers can customize a navigation technique. First, parameter level adaptation. The designer chooses a specific navigation technique, for example, continuous steering, and simply modifies predefined parameters, such as the speed. The designer can also specify non-numerical choices, for example, which button must be used to navigate, but available choices are predefined. The second level is user-defined adaptation. In this case, the designer also chooses one of the predefined metaphors and provides the source code defining the mapping between user input and locomotion output. Therefore, designers are completely free to specify the mapping with the only limits imposed by the selected metaphor. Our current prototype supports three major navigation metaphors: free teleportation, teleportation with predefined targets, and flying or walking through continuous steering. Let me describe the basic behavior of these metaphors. In free target teleportation, the user points at any target location and the application automatically moves the viewpoint to that target location. The teleportation points metaphor is similar to free target teleportation, but target locations are limited to a predefined collection of targets. Finally, the walking, flying metaphors allow users to walk, grounded navigation, or fly with no high constraints through the virtual environment using a continuous steering technique. A key issue for fast experimentation is to allow users and interaction designers to quickly change these parameters through a graphical user interface. Our prototype includes two different UIs. The 2D UI is available anytime the application is not in VR mode and can be interacted with traditional interaction devices, for example, mouse and keyboard on a desktop PC. Conversely, the VR UI is available only when the browser is in VR mode. Thanks to the WebXR emulator, designers can test immediately any adaptation by just switching into VR mode. So users are not required to put the VR headset on and off every time they modify some parameter. Let me discuss in more detail how users can adapt any technique by just modifying the parameters. I will discuss only free teleportation. The options that can be adjusted were decided taking into account well-established analysis on the different subtasks involved in selection-based techniques. We now briefly describe the different options. The first group is concerned with the target selection part. Starting pointing refers to which user input initiates the selection and causes the selection ray and/or the selection target to be shown. Available choices include, for example, specific buttons of the controllers, as well as an always active option. Pointing direction specifies how to compute the base pointing direction, and available choices include the controller's forward direction, the user's head, and the user's torso. Concerning the maximum distance to teleportation, we allow the user to limit the maximum distance for selectable target positions. This is especially suitable for curved arrays. Ray type refers to whether to use a straight line segment or a curved selection ray. Curved rays provide a more equally spaced mapping between ray orientations and target distances. Confirmation refers to which user input confirms the target selection. Available options are similar to those for start pointing. The second group of options refer to the actual teleportation part, as well as field of view reduction to reduce motion sickness. Teleportation speed is the camera speed towards the target, or 0 for instant teleportation. Field of view reduction fade-in is the time, usually a few milliseconds, to gradually reduce the field of view. Similarly, the field of view reduction type is how much the normal field of view must be reduced during gradual teleportation. Finally, we allow users and developers to define programmatically their own mappings between user actions and navigation control. The user is free to provide JavaScript code for a collection of functions defining all aspects of the navigation technique. In this example, we are providing our own expression to compute the teleportation speed. Again, we can test immediately the resulting behavior in VR mode. This seems to be quite slow, so we are going to modify the expression to speed up the motion and test again. One can argue that developers and user interface designers can write these pieces of code just as part of their JavaScript modules. However, our application allows these functions to be written directly on specific user interface components. Furthermore, the functions can be edited at any time and are evaluated at runtime. For example, we can navigate to a specific room and test different mappings immediately without reloading the application. This method makes testing iteration cycles much shorter and thus allows for a more comprehensive testing of different mappings in varied situations. Let me describe the kind of custom functions experimenters might provide to define precisely the behavior of teleportation. We indicate the expected JavaScript return type within parentheses. Unless otherwise stated, these functions are invoked automatically every frame. Starting pointing returns a Boolean value. The target indication will be initiated as soon as this function returns true. The pointing direction returns a 3D vector. This is the function providing the 3D vector to be used as pointing direction. Confirmation should return a Boolean value, and the teleportation target is confirmed as soon as this function returns true. And speed is a function providing the speed for gradual teleportation. Notice that custom functions roughly match the breakdown for the different configurable options. Alternative factorizations exist. For example, we could require the user to provide a single target vector3 function returning the selected target, instead of asking separately for the target selection subtasks. Our factorization, though, provides multiple advantages. On the one hand, it is close to that of the user interface adjustable options, and thus easier to understand and remember. On the other hand, the proposed factorization facilitates code reusability and simplifies development since empty custom functions take the default behavior. For example, the experimenter might choose to provide a custom function just for the pointing direction while reusing the default behavior for the rest. Let me now discuss a pair of use cases that benefit from fast iteration cycles for optimizing navigation. The first case is a medieval church with mural paintings. The goal was to provide intuitive navigation for art historians to explore the mural paintings of Sant Quirze de Pedret using a standalone VR headset. The designer used Google Chrome running on a desktop PC for testing different navigation techniques and an Oculus Quest for fine-tuning. While using the desktop PC, we used the WebXR API emulator. The tool allows us to quickly discard continuous steering techniques due to motion sickness issues. We tested large field of view reduction, but this prevented users from seeing the mural paintings above the line of sight, for example of the apses. So we found field of view reduction not appropriate during a steering-based navigation. We thus opted to default to a free teleportation technique using the handheld controllers for selecting the target position. Parameters such as maximum distance and gradual teleportation speed were also fine-tuned to the reduced size of the charge. In our second use case example, our goal is to let art historians to inspect Sant Quirze de Pedret surroundings and architecture, this time emphasizing on the outdoor model. Free teleportation was tricky because the church is on the edge of a long and jagged hill mountain at the foot of the Pyrenees. On the other hand, the scan locations were readily available, so we decided to test and fine-tune teleportation using as predefined targets the scan locations, which also guarantee high-quality viewpoints of the model. In conclusion, we have discussed the benefits of a web-based tool for quickly designing, testing, and comparing navigation techniques for virtual environments. Our hypothesis is that if testing iteration cycles are very short, designers can fine-tune the default parameters of the chosen navigation technique to the specificity of the 3D environment, the user task, the target users, and other contextual issues. Our tool supports the design of inclusive VR experiences in the sense that fast testing allows designers to offer a catalog of preset navigation techniques to cover the largest possible audience, and because the user interface allows end users to further customize navigation options to suit their needs. As future work, our first priority is to further evaluate the usability of our framework. We want to evaluate if the development of custom functions is fast and suitable for developers. We also wish to add further high-level methods to facilitate writing such functions with a few lines of JavaScript code, including, for example, filters to smooth out user input. So that's it. Thanks for your attention.